Hi again, and welcome to Lesson 10 of Android App Development Training course. Today, you will understand the basic principle on how to organize your code and properly structure your Android apps. This is commonly known as separation of concerns. We'll cover some of the topics like Lifecycle Observer, viewModel, LiveData, and companion object. We'll learn this as we build our demo application. It is a simple My Data Plan app that allows us to add or load either 100 MB or 250 MB mobile data on top of our existing data plan. This application must be lifecycle aware and should retain its UI state even after an orientation change. Although we have accomplished a similar functionality before in Lesson 8, but our main objective here is to write this app by following the basic principle of separation of concerns. To start working with our app, I already have a layout that consists of an image view, a header message with ID of txt message, another text view to display the remaining mobile data, its ID is txt data, and the two buttons for 100 MB and 250 MB load respectively. If I run the app, you can see that it doesn't do anything yet. So far, I haven't added any code to our main activity class except for this viewBinding variable. In Lesson 8, I've discussed how to handle activity lifecycle events with code written in the activity. The common pattern that we do is to implement the actions of the dependent components in the lifecycle methods of the activity, like the onStart and the onPause callback functions. However, this pattern leads to a poor organization of our code. It makes our activity class messy and hard to maintain. To improve our code organization, we can use a lifecycle-aware components provided by Jetpack. The Android X Lifecycle package provides classes and interfaces that let you build lifecycle-aware components that can automatically adjust their behavior based on the current lifecycle state of an activity or fragment. To use it in our app, we must add this Android X.lifecycle dependency. The latest version at the time of this recording is 2.3.1. You can change this if you are using a newer version. And then, in my base package, I'll create a separate class I'll call myObserver. This could be any name that you want, but the important thing here is that this class should implement the Lifecycle Observer interface. This interface doesn't have any required functions, but instead, it relies on annotated methods called onLifecycleEvent. Our goal here is to slim down our activity and move code that reacts to lifecycle events to this myObserver class that is not dependent on specific callback functions in the main activity. So, for example, if I want a function that reacts to onCreateLifecycle event, then I need to add this onLifecycleEvent annotation, and inside this parentheses, I can specify any lifecycle event using one of these constants. I'll choose the onCreate, and then I'll duplicate this code, and when you create a function that reacts to any lifecycle event, the function name could be anything you want. It doesn't have to be onCreate, onStart, or onDestroy. Say I'll give it a name of onClose. But what important is this, the onLifecycle event annotation, and this function will react to onDestroy lifecycle event. I'll create another function that reacts to onStart, and I'll call it show with a log tag saying screen is visible, and one last function that reacts to onStop, and I'll call it hide, and change this to screen is hidden. In my main activity, I can already remove these callback functions. Now, to use this myObserver class, inside this onCreate function of our main activity, I'll use a property named lifecycle. This lifecycle exists because the appcompat activity implements an interface called lifecycle-owner. It has a function addObserver, and then I can pass in an instance of myObserver class here, and that's it. Now, we can test our app by tracing the log through this logcat window. As you can see, when the app launches, two of the functions react to the onCreate and onStart lifecycle events. Clicking the home button, the function hide reacts to the onStop lifecycle event. I'll open the app again and the show function fires. Finally, closing this application executes the onClose function that reacts to the onDestroy lifecycle event. Visually, we haven't done any major changes here, but our main goal why we do this is to apply some of the best practices to keep our UI controllers lean. This is our activity or fragment. For your future references, here are some of the use cases that may require you to implement this approach. When you start and stop video buffering, starting and stopping network connectivity, pausing and resuming animated drawables, or switching between location detection technique. For this app, we want a functionality that displays the remaining mobile data of the user, and as this load button 100 is clicked, it should add 100 MB and update the remaining data displayed. I'll wire this button 100 to the setOnClick event listener and simply display this string literal of your remaining data is, and then a fixed value of 100 MB. Now, let's run the app. And I'll open this logcat window. Same as before, the two functions in the myObserver class reacts to the onCreate and onStart lifecycle events. And when I click this button 100, it displays the corresponding message and the remaining data of 100 MB. But then again, similar to the issue that we addressed in our previous lessons, changing the device orientation destroys the activity and recreates it again. This resets the UI state of our main activity. I can click this load button again to update the display, and similar thing will happen the moment I rotate the display back to portrait. I'll delete this code for now, and I'll introduce you to another class that you can use to manage your UI-related data in a lifecycle conscious way. Unlike with the desktop app, where there is only one entry point for an application and run in a single monolithic process, Android apps have a much more complex structure. A typical Android app contains multiple app components including activities, fragments, services, content providers, and broadcast receivers. And at any point during the app interaction, the user could be interrupted by a phone call or a notification that may interrupt the ongoing process. After the interruption, the user expects to be able to return to and resume to whatever he or she is previously doing without losing the current app state. This app hopping behavior is very common on mobile devices, so you must write your app that can handle these flows correctly. Consider this following diagram. When designing and organizing your app, activities and fragments should depend only on a view model. These repository modules handle data operations. You can consider repositories to be mediator between different data sources, such as a persistent models, web services, and cache. They provide a clean API so that the rest of the app can retrieve this data easily. They know where to get the data from and what API calls to make when data is updated. So, let's start with a view model. A view model purpose is to handle the business logic and provide data for a specific UI component, such as activities and fragments. View model doesn't know about the UI components, so it is not affected by orientation change, such as recreating the activity when rotating the device. To understand the scope of the view model, consider this example. With a view model associated with an activity, when the activity is first created, so is the view model. But then, as the device is rotated and the activity is destroyed and recreated, the view model remains in memory. And only when the activity is destroyed permanently, does the view model onCleared method gets called and it goes away. So, to use viewModel in our activity, let's update our build.gradle file to include another dependency, the activity-ktx library. I'll sync the project. Now, although we can create our model class directly in our base package, but what I'm going to do is to create another package here, and I'll call it viewModel. Now, inside this new package, I'll create a new class with the name main_viewModel. This class should extend the viewModel class, and this one requires a constructor that must be initialized. In Kotlin, a primary constructor cannot accept any code, unlike with Java. And to initialize something in this class, I can either use a secondary constructor or this init block, which is quite similar to a constructor. This init block gets executed when this class is instantiated. For now, I just want to print something in my logcat window that says main_viewModel is created. And then, to reference this main_viewModel in our activity, I'll create a local variable named viewModel, and then I'll use the extension function from the activity-ktx library by calling this by viewModels. And then I have to specify the type, which is our new class main_viewModel. There are few things that you need to understand when using this extension function. I'll press Ctrl and click this link. You can see that this function returns a lazy viewModel, which means the viewModel will not be initialized until it is actually needed. To understand what I'm saying, let's check our logcat window and run our app. I'll clear the log first. And as you can see here, the same main activity is created and screen is visible messages appear as the app starts. However, the init code block was not executed. It only indicates that the main_viewModel is not actually created because it is not being used by any activity. Now, I'll declare a public variable, message, and then I'll set it to type mutable LiveData. This is of type string. I'll bring in the import. Mutable LiveData is usually used inside a viewModel, which in turn, the viewModel only exposes the immutable LiveData object to the observers. These are your UI class, the activities and the fragments. And then, I'll create another function here that sets the value of this message mutable LiveData, saying new message from main_viewModel. I'll copy this code and print this message to the logcat. Now, there is an error because this message.value could potentially hold null value. And since we are sure that it has a value, we can put this assertion operator to indicate that this will never be null. And going back to our main activity, I'll call the viewModel.loadMessage function. Now, let's see if the message gets printed in the logcat window. Let's run our app. And as you can see, the init code block is now executed, together with the loadMessage function. It means that our viewModel is only initialized the moment we use it, and it is created together with the activity that references it. I'll stop the application by pressing the home button and then restores it again. During these states, our viewModel is still active in memory. And as I rotate the device, the main activity is destroyed and recreated, and the call to the loadMessage function of the viewModel is also executed. But the viewModel was never recreated. It still persists in the memory. So, as a takeaway, if you have important UI-related data that you want to observe and be displayed in your UI regardless of the activity states, then the viewModel and LiveData is your way to go without burdening your primary UI controllers such as fragments and activities. I'll change this message value to your remaining data is, and instead of printing this to the logcat, I'll display it in my text message of my main activity. Again, I'll access my viewModel reference variable and access the message mutable LiveData. By using a LiveData, we can observe any changes that happens to this variable automatically. This observe function requires a lifecycle owner, so I'll pass in this activity, and then the action that we want to take place when the data is changed. Again, this is a lambda expression, and the action that we want is to set the text attribute of our text message to the content of this message variable, and it is represented by this parameter it. So, let's run and test our app. And as you can see, the message "your remaining data is" displayed as the main activity is created. This happened because the message LiveData has been changed already by this load message function call. I'll cut this, and what I want to do is only change the message once I click the button 100. So I'll paste the function call here. And now, notice that the header message hasn't been changed, and the LiveData message inside our view model will only change once I click this button. And in effect, our observe function is called automatically to update our UI component. And as I rotate this device, the main activity is recreated, but the value of our LiveData in our view model persists. Thus, the UI value displayed remains the same. Recall that in our previous activity, we were able to accomplish almost the same behavior by using this save instance state bundle. Well, this is good as long as you're managing simple data such as string or primitive values, but when restoring something more complex and memory-demanding data such as bitmaps or maybe some asynchronous process that is currently running, then it is recommended to use the combination of viewModel and then LiveData. Going back to our viewModel, there is one problem here that I want to point out. This mutable LiveData is publicly declared, which means this can be accessed directly by any activity that references this viewModel class. And it could be accidentally or intentionally set its value to anything. Notice that when I run the app, every time the onCreate function is called, it sets a new value to this message mutable LiveData of anything here, and automatically reflects back to our text view. I can change the message by clicking this button again, but the same problem occurs when I rotate this device. If we are going to follow the principle of encapsulation, we must make this field private, and this becomes inaccessible in our activity. Now, I'll rename this private field by pressing Shift F6 and change it to _message. This is just a naming convention to denote that this field is private. So, in effect, our message field can no longer be recognized, and this is expected. So, to expose this message data to the activity, but it is meant only to be observed, I'll create a public, which is the default access specifier, and we can simply omit it. Val message, now this time, it is of type LiveData. And I'll assign this _message mutable LiveData. I'll bring in the import. So, by using this LiveData, it can be observed by any activity to update any UI component, but it cannot be modified. This properly protects our mutable LiveData from being changed directly in the activity. Now I'll comment out this code and test our app again. Same as before, when I click this button, the text message is updated, and even if I change the device orientation, the LiveData still persists. So by using this pattern, I can accomplish the rest of the app's functionality, I'll declare another private variable underscore data, and this mutable live data is of type int, as well as this private underscore load. This is of type int as well. And then I'll duplicate this public live data twice and change the variable name to data of type int and assign the private underscore data to it. I'll do the same thing with this load live data. And now in our init block, I'll move this code. Also, I'll initialize this underscore data to a value of 120, as well as this underscore load to 0. Actually, you can do it here as well. So I'll simply remove it here. Then I'll change this function name to load data. Now the functionality that we want to achieve here is when I click this button 100, it adds 100 MB to the remaining data. And when button 250 is clicked, then 250 MB will be added. What I'm going to do here is to use this load data function for the buttons. So I'll create a parameter load type of type int. This will identify which button initiates the call to this function. And inside this function, I'll use the when operator. I'll check when the load type is 1, then it returns 100 and assign it as the load value. When the load type is 2, then it returns 250. Else, the load value is 0. So to update the remaining data, I'll get the data value and add it with the load value. Again, I'll assert that this is not going to be null. Now, in our main activity, I'll change this to load data function call and pass in a load type of 1. I'll duplicate this code for button 250 and change the load type to 2. Similarly, I'll apply the same code pattern here to update the text data when the data is changed. So I'll observe the viewModel.data and then update the txt data to the new data followed by MB. So now let's check if our app is working. And so far it looks good. The initial message and remaining data is displayed accordingly. And when I click the button 100, the data in the view model is changed and the txt data is updated by observing the change. Similar thing should happen when I click this button 250. Now, the good thing about this is that viewModel is independent from the activity. It persists in the memory even if the activity is recreated, like when I rotate this device. I'll add another message here to display the load that was added. So, I'll observe the load as it changes. And if it does, I'll display it in a snack bar message saying, "You have successfully added," and then the load in MB. Now, instead of copying this one and then pasting it inside this button 250 lambda expression, what I'm going to do is refactor this code and then give it a name of addLoad. Now, I can simply replace this one with a call to this addLoad function. But instead of having a fixed load type of 1, I'll add another parameter here, load type, and use it here instead. So now, when I call this addLoad function, I need to pass in the viewModel and then a load type. And again, let's test our app. When I click this button 100, a snack bar gets displayed with a message of, "You have successfully added 100 MB. Same as when I click this button 250. And of course, our remaining data is updated even as the device orientation changes. So, in addition to this code structure that we have in our view model, you might want to move some of the codes that involve generation or retrieval of data from any data source. And for example, this message and remaining data might be coming from a web service or a cache, and we can use another class to handle the processing of this data. I'll illustrate this with the use of a simple helper class. I'll create a new package I'll call util, and then create a new class inside it. I'll call it main helper. I'll create a companion object inside it, and basically, companion objects are singleton objects whose properties and functions are tied to a class and not to the instance of that class. This is somewhat similar to the static keyword in Java. I'll create a function here, getMessage, with a return type of string. Now you can have codes here that retrieves a message from any data source. But to make it simple, I'll just return a string literal of your remaining data is. Similarly, I'll create another function, getRemainingData, with a return type of int. Again, you can have codes here to retrieve the remaining mobile data from any data source. But to make it simple, I'll just return a value of 120. And then going back to our view model, I can replace this with a call from our main helper class, getMessage function. I'll do the same for this data.value. I'll get it from the main helper getRemainingData function. And when we run our app, the same functionality can be achieved. So to summarize the code organization that we did, all of the data management code is encapsulated in the view model and in the main helper class that we have created. Each class is taking care of only its task, and it is unaware of how the other classes are using its information. The main helper class creates the data but doesn't know how it is going to be used. The view model acquires the data and publishes it but doesn't know how it is going to be displayed. And the main activity class receives the data but doesn't really know where it came from. And this is the pattern known as separation of concerns. It results in an application that is easy to maintain over the long period of time. And now, for our programming challenge, try to create a minimalist shopping cart app that displays the following information using viewModel and LiveData: the product description, product price, default order quantity of 1, and the delivery fee. The user can then increase or decrease the order quantity, and when the button checkout is clicked, the total amount is displayed in a stock bar. The total amount is computed as the product price times the order quantity plus the delivery fee. Another business logic that you need to implement is that you can no longer decrease the order quantity below 1. The maximum order quantity should not exceed 10, and the delivery fee will be 0 or free when the order quantity reaches 10. And of course, the current UI state should be restored as the device orientation changes. Take note that when doing this app, you must not include any business logic or data management inside your UI controller or activity. You must implement these codes in its corresponding classes. And again, thanks for watching. And if you learned something of value here, please click the like and subscribe button for more programming tutorials. This is Joe Edgo, and hope to see you in the next video lecture.